What I would like to talk about today is about the part 4, which is net-centric operations. You may recall 3 weeks ago I talked about data strategy. Part 4 is net-centric operations. In the spring I will be talking about information assurance and enterprise services. With that setting, I want to point out that I will concentrate tonight on the business mission area. It's a vast subject covering more than $31 billion worth of expenditures. I will concentrate on the piece which deals with business, and therefore will concentrate on the discussion starting with 3 case studies about transformation. In other words, before discussing the directions of the Department of Defense, I will briefly illustrate what I mean by transformation. The first case I have here is a case study from IBM. It is the latest data we have from IBM. They are spending $3.9 billion for IT, and they have so far achieved an 18% cost reduction. The way we illustrate the transformation in case of IBM and the $20 billion that they claim they have saved was that they have basically cut down the purchase order process time, the sources of procurement. They have greatly increased the electronic purchases, enabled suppliers and electronic catalogs. I must point out that the thrust of the IBM transformation has dealt with the upstream part of IBM, of the logistic chain. They have not dealt into the inside piece. They have looked from the upstream piece because this is where the biggest opportunities were located. It is important to understand that this is a partial picture. You must also understand that transformation takes place externally, internally, and then downstream in supplying the customers. We don't have that information here. Just to show you what is some of the consequence of such a transformation is I'm comparing IBM in 2004 and the Navy, whom I've picked as an example. They're roughly comparable, by the way. The only difference, of course, is that the Navy has a much larger number of people. But the significant difference which the transformation concentrated on was in reduction in management layers, the total number of networks, and this is very important. IBM basically has gone to one network that ties together the supply chain globally. The total number of network in the Navy is unknown. The best estimate, for which I cannot vouch, by the way, this is secondhand data, is that it is more than 500 and has been estimated at 850. The other thing, of course, is that IBM has materially reduced the number of applications, materially reduced the financial management applications and the HR applications. The reason, by the way, why the IT applications and the financial management applications and the HR applications are still so big, and I understand they are in the process of slimming that down, but in 2004, various countries still depended on their own financial and HR applications, and the reason was that there was no way electronically centralized to provide the support for these services in the outlying companies, in the outlying countries. Also, IBM has gone through a substantial number of acquisitions. So that explains, by the way, the large number of IT applications. Of course, compared with the Navy, this pales insignificance. So that really gives you a rough picture of what a transformation looks like in case of IBM. Let me now go to another transformation. This is a totally different transformation, and that has to deal with Visa. When you slide out of your pocket a Visa card, that card is read into a network, a Visa network ultimately, goes through a number of hops that redirects that inquiry to find where is the bank where you are trying to charge your money to. They also check, of course, your credit, and in that process then are able to go through a rapid process of verifying the credibility of your Visa charge. Now, the reason I'm showing you this is an example of mature transformation is to show to you what it entails. Any one of over 1.3 billion Visa card can come in anywhere in the world, and it can be accepted by more than 24 million input sources in over 160 countries. So you have to now understand we are talking about a massive scale. These countries have data systems and bank systems in different languages, in different protocols. The ATMs are different. And therefore, the important thing in case of this kind of a transformation is how do you take data from millions and actually billions of disparate functions going to disparate location, going to different banks, and are able to handle that response time in slightly over a quarter of a second, certainly never more than 2 seconds. That is an awesome achievement. The interoperability is achieved basically by Visa creating in a number of data centers a big data grinder where they take disparate information, homogenize it centrally, and then spew it out again to the banks and into the environment. This is all done with a global systems integration staff of 200. Now, why am I showing you this thing? I'm just showing to you as an illustration of what transformation can do. This is a mature, transformed organization. They are now reaching for other opportunities. But this is an engine which is perhaps one of the largest, fastest engines in existence, which successfully integrates thousands and thousands of sources of information, homogenizes them, and then spits them out again until they find themselves in your monthly statements from your bank, if that's the way your Visa operates. The technologies that Visa applies is massive parallel computing, and the fundamental principle that only valid data, there is no data pollution. Remember, 3 weeks ago I talked about data pollution. There is no data pollution. The system cannot operate with polluted data. So there is a whole filtration system. Bulk of the Visa system is actually a filtration system that filters out the data and normalizes it. The code is then assembled from components, and then the services, a variety of services are provided depending on the kind of services the banks buy. Again, the only thing that I have to say about Visa, which is unique, it is that it is a limited set of application. Yeah, I've gone from the IBM case now to a Visa case, purely to demonstrate to you the scope and the scale of a transformed operation. What I want to concentrate on tonight is the most likely and the most appropriate example to be considered as a case of transformation that may have relevance to the Department of Defense. And that is the ongoing program by Hewlett-Packard. The current IT budget is $3.5 billion, and so far they are clocking in 21% cost reduction. And so the transformation of Hewlett-Packard is more like the kind of commercial environment we encounter today, both in private commercial business as well as in federal agencies. Now, let me give you the vital statistics about the Hewlett-Packard program. The key underlying driver behind the Hewlett-Packard program is the material reduction in applications. You have to reduce applications if you want to transform a business. You cannot continue having a multiple payroll system. You cannot continue having multiple financial system. And by the way, while this is going on, the company is making acquisitions. When the acquisition comes in, they are handed over a set of application, and that's it. Now, in order to achieve this kind of a transformation, they reduced the number of servers from 19,000 to 10,000. Now, this may not look like a very impressive number, but you will find that it is extremely potent because the capability that is being delivered is materially different. By the way, servers are cheap. So the button that you push is not server reduction. The button that you push, you put massive amount of computing power. The button that you push is the application reduction. Now, what you want to do, of course, is you want to take the servers and increase their utilization. And the reason you want to increase it for reliability and for security. In other words, you do this so that each application is processed at least 3 times as a way of achieving the redundancy. You know, every development site is an invitation for trouble. You put programmers into a room and the programmers will create code, regardless why, how, they will. So a part of the reduction of application strategy is the consolidation of the world site for development and the massive consolidation of data centers. Now, that is just part of the story. The other side of the transformation is the creation of a massive parallel database, which is a service-oriented architecture accessible. The idea here is to have a warehouse. Now, this is not one warehouse. This is a multiple warehouse. But in order to be able to get interoperability and look at how the personnel system interact with the financial system and so forth, you need a database out of which you can then extract information rather than have to go and hunt individually into each database for information. This is very important, and the reason why this is important is latency. you want to have quick response time. If you have databases in individual applications, and then you want to combine and draw from various databases and extract and discover what is in the various databases in order to get an answer, the time that you will spend in doing that is going to exceed the tolerance of the people to operate the environment. And therefore, the data warehouse becomes a very important element. Item 7 may, in fact, be the single most important item. And this is one that I scratched my head over. Frankly, I don't believe it, but I'm told now from 3 separate sources this indeed is so. What really happened was that the IT workforce consisted of 80% contractors and 20% organic people. And the contractors were located at the 100 IT development sites. So you had lots of people doing lots of things at lots of locations. Their hope, by the way, they have not as yet achieved the 8,000 reduction, they're well on their way, is to basically eliminate work, eliminate the number of applications, and thereby go to standard components and standard databases out of which they can then extract information without having to design infrastructure for each individual application. And of course, lastly, once you do all of that thing and you push all of these buttons, you get the ability to devote 80% of the staff to new projects, which is precisely the other way around as currently is the case. The point I want to make here is that if you want to do a transformation, there are many buttons that you have to push. You cannot just take one variable and hope that that variable will give you the desired results. You have to harmonize and in a concerted way go through a broadly diversified, distributed approach. And Hewlett-Packard is doing that. I have here a chart which you may not be able to read, but this is purely my evidence. This is taken out of HP material, and it just shows you how you go from 10,000 applications to 1,500 applications, how you go from the servers, how you go to the data center. This is the schedule. I have much greater detail behind the schedule. It is my understanding that as of 2006, HP is tracking and is making progress as projected, which is, in my view, quite unbelievable. Now, where is the payoff? Where does HP make the money? They make it in material, procurement, product redesign, supply chain. Again and again and again, it's the supply chain. It's not the cost reduction in personnel, although necessary. It is not the cost reduction in finance. In other words, the ROIs for this program are in materials management. And it is my belief that when I look at the numbers of the Department of Defense, the big pie is in materials management. And as you could see, we are talking now about annual targets of savings. And by the way, I've just looked at the latest financial report of Hewlett-Packard. It's outstanding. As you know, there's been a ripple in the organization. That's over. We have new management, and they apparently are moving swiftly in the process of trying to achieve these cost savings. Now, I think this may be one of my last comments about Hewlett-Packard, and that has to deal with what I consider the next generation data center, I hope you can read it, basically says that the entire environment is saved and operated by a shared server pool. In other words, you don't designate servers to individual applications. You set up a shared server pool, and you set up a shared storage, and you support the entire enterprise from shared resources rather than from individual resources for application, for case. Let me give you just a small example of the Hewlett-Packard example, namely what they are achieving. They have one personal information system. Now, is it the same for everybody? The answer is no. What they have is a single personal information data warehouse, and then extracted out of that from a portal. And the portals are different. But as you understand the way how you do coding, a portal kind of extraction is a totally different class of an effort than coding an application. The big payoff, of course, comes out of cutting 84 procurement transaction system and great emphasis on portal capabilities, which then offer capabilities for user-initiated inquiries. The idea is to move out to the user the ability to ask questions rather than ask for reports. This is a very significant development. Now let me conclude the Hewlett-Packard case just by giving you some indication of the kind of variables that I would be looking at from a standpoint of an architect. And well, how does HP and the Navy compare? Let me start from the bottom. HP will be spending 37% of its cost on an infrastructure. The Navy spends over half. The maintenance is eating up the Navy alive. 36% of the total Navy budget is going for maintenance. Hewlett-Packard goes 13%. But the payoff comes from application innovation and from agility. The ability to have money available to do new things, to do innovation, to make money, rather than maintain the environment. The lesson to be drawn from Hewlett-Packard, I think, is awesome. It's clearly an indication and an insight that is applicable to not only the Navy, the Air Force, the Army, but also to any public sector agency. All of these agencies have the same characteristics. Too many applications, too many servers, too many data centers, too many databases, no shared servers, no shared data resources. And that is really then the reason why transformation is so important, because transformation allows you to do all of that. So having given you now 3 examples with different implications of what transformation is all about, let me now go into a Navy case study. Again, let me just summarize. These are systems, these are major systems, and you must understand, systems then break down into applications. But as you could see, the Navy has 798 major systems which they report to the Office of Management and Budget. Here is how the money is spent. 54% goes for the infrastructure, 29% goes to the warfighter, and then you have a scattering going down to the various applications in logistics, human resources, other, and acquisition, and so forth. The good news is that it's only $6.3 billion. The bad news, it is not $6.3 billion. The bad news is that there is so-called inefficient or virtual or stealth spending that nobody knows what it is. But people have on their desk mainframes called desktops, fat desktops. And once you give somebody a mainframe on their desk, they are going to have unofficial spending which creates applications. And that will not show up any place because it's just labor that gets absorbed. And labor that is contracted out, not as IT, but contracted as other things. So that is then the picture of the environment. The thing that I want to focus on is the infrastructure. Now, those of you who are not acquainted with the Navy's spending should know there's such a thing called as NMCI, Navy Marine Corps Information System. It's a $8.5 billion expenditures contract with EDS to basically provide desktop support. And what I'm showing you here is the frequency distribution of the environment, which shows how the money is being spent. And so that you interpret this thing correctly, let me move from left to right. You see from 0 to $2 million, you have approximately 350 projects. In other words, there are 350 projects in the Navy that we know of. By the way, the unofficial projects are not only on the radar scope. We are spending less than $2 million a year in 2007. That means that when you look at the distribution of the systems, you find that the bulk of the applications in the Navy are small projects. And by the way, these projects all require some kind of a administrative overhead. So if the budget is $2 million, and particularly since most of these projects are contracted out, the administrative cost is quite horrendous. NMCI is huge, but NMCI basically does desktop management, basically, and provides an infrastructure. It does not take care of the bulk of the 765 remaining major projects. And therefore, the problem is that when you look at how the money is divided, you find that 571 information environments are really still on their own, unrelated to NMCI, unconnected with NMCI, and NMCI is taking a big bulk, but is not really making an impact on HR, and particularly not on logistics. I want to digress for a moment to point out that what I'm discussing here is strictly Navy spending. There are substantial additional money being spent outside of the Navy in the logistic, in agencies. But I will not discuss that in there, other than just emphasizing that NMCI is taking a huge amount of available money, delivering little. It's not delivering in any way the kind of transformation that would meet any of the criteria that the Hewlett-Packard case would illustrate, for instance. You really shouldn't look at this thing, but here are 45 out of 470 infrastructure applications that are for this and this, 12 million for this, 10 million for this, 2 million for this, and so forth. It's a huge amount of money being expended for programs which are still in no way being integrated or put together through the NMCI environment. By the way, the same kind of a distribution you see when you come to functional applications, which is personnel, finance, and so forth. Let me give you an example here. When you look from left to right, you will read that there are 400 projects with a budget of less than $1 million that is being spent within the Navy. In other words, what you have is a fractionated effort, small pieces all over the place. And as you could see, only a few programs are large programs. Again, this is totally different than anything you see in a transformation, whether it is in Visa, IBM, or Hewlett-Packard, which are characterized by compressing applications. Here you have a proliferation to a large extent. And again, you have a long list. They're all good projects. I'm sure they are all justified. I'm sure they all have a sensible reason and a rationale, but they are not supportable. Again, here are logistic application. Again, 10 million here, 21 million here, 2 million here, 1 million here, and so forth. So you have all of these applications which are still hanging out there, waiting to be transformed. In other words, when you look at the Navy, you say, my God, where have you been, guys? You know, you are not transformed. You are not even started on a transformation because you have that many applications out there. So what are we then talking here about? We are talking about the fact that when you look at the underlying economics of transformation, you have to discriminate between infrastructure and between applications and then local capabilities. The local capabilities in my book are basically applications which are driven by means of a portal. This is something that you locally construct and execute and obtain. The important thing to realize is that maybe as much as 80% of all code in an application is in infrastructure, which is the foundations, the communication, and the distributed environment. The objective of the transformation in the Department of Defense, and this is a highly summarized form, is to basically say we are going to take 3 areas. And in the area that we know about, this is for the time being as defined by NII, which is the Chief Information Officer, we are going to take the infrastructure and standardize the infrastructure and support from the infrastructure all of the system so that the system only perform their dedicated functions, but the infrastructure, which then can be consolidated in terms of data centers, in terms of communication system, in terms of security and so forth, will be shared and common. It will be a utility. Now, with this design, then, the directions are clear, and the issue then is how do you take this environment and create what's called a net-enabled environment, which is the current objective of the Department of Defense. So the vision of the transformed Department of Defense is to deal with the increased impact of warfare, which is becoming very volatile, very undeterminate, very much subject to unpredictable development, is to deliver the power of organization through agility, namely the rapid ability to change. You must understand much of the information system that we have currently in place is Cold War vintage, where we dealt with a stable enemy. We now need an information system which is agile, which means that you must have the data available, the networks available, the security available. You don't worry about it. It's an underlying utility. And then you have this enabled in the network from which you can then extract information and data. So the context which is currently being proposed for the Department of Defense is to deal with uncertainty. In other words, the reason we are designing systems the way we are designing is to deal with uncertainty. And since we cannot plan for an uncertainty, we want to have what's called agile systems, systems that will bend, reshape, adapt, and transform, plus, very importantly, creating sufficient efficiency so that we have spare manpower within limited budgets to create new applications. So the net-enabled sharing environment is necessary to discover, access, trust, and use data information that support the mission objective. And that means fewer applications, but moving the applications out into the portal level, but the basic applications are not deeply embedded in the environment, but you have a few number of applications that feed your fundamental data repositories from which you can then extract with little expenditure the kind of flexibility that you require. And that means that you have to have faster decisions, and that means also that it calls for rapid response. It means very high levels of availability at reliability levels which are very high. They are in the high Six Sigma reliability levels. Now, I don't want to bore you through this thing. As you know, all of these lectures are going to be posted on Google very shortly. This particular lecture is also going to be available. All I want you to know that to do a net-enabled information sharing environment, there are lots of buttons you have to push. I'm not going to go over these buttons, like post in parallel and so forth. These are all discussions. They cannot be elaborated in sufficient time. All I want you to know that the network-enabled information sharing environment consists of many, many, many activities and many systems engineering artifacts being put in place simultaneously. The underlying idea is the gig. It is the idea to have a globally interconnected end set of information capabilities. It is more than just a network. It includes systems, services, and applications that perform the kind of flexible environment that our army needs, our soldiers need. It means that it has end-to-end information capability, and most importantly, it greatly increases the reliability and the secure access of information. Now let me now conclude with some comments. They are just random comments. They are not exhaustive, just some observations about the grid. Now, the grid basically is the internet. That's what it is. By the way, internet is a very dangerous place to live on. So now we have to live in something that looks simple but is extremely complex and dangerous. Clearly, internet offers lots of advantages. Any properly configured computer can act as a host for a web page. Any of several hundred million computers can be viewed as a personal web page. Any of several hundred million other computers can be connected to any other computers. So internet does all of that thing. The question is, well, how do we do that? How do we transform the inside of the Department of Defense, the thousands of applications, and move them into the internet securely, reliably, and responsibly? Well, the problem with internet is that it's a mess. This is actually a picture of the ISP connections in the northern part of the United States. You have unbelievable number of links going from point to point. There are so-called ISP, information service providers. Some of them are high-performance links, some of them are low-performance links, some of them are high up on the node, some of them are particularly out in the boonies, in the localities which are downstream from an application. The problem with the internet is hops, and I want to acquaint you now with hops. This is a very important thing for you to understand. When you are dealing with an application, when you are dealing with an environment, you have to figure out how many times your transaction will have to come from your desktop until it gets to where you want it to go. This is a very fast application. It's only 185 milliseconds. This is one of the fastest applications. But I'm just showing you it went through 9 hops in order to get to a point where it was trying to retrieve a piece of information. Let me repeat this. You are at your terminal. You fill out a request on the website. You push a return button. And in a second of the most, depending on your speed, you will get a response. That transaction has gone through a number of hops. And depending on where you are, depending on the point of origin and the point of destination, you may be as much as 25 to 30 hops away. And you may have hops which don't take more than 100 milliseconds. Once you start thinking about hops that way, you say, my God, I want to go somewhere globally. In other words, I am in Arlington, Virginia, and I want to make an inquiry of a database in Iraq, or vice versa. Okay? Depending on who conveys this information and how that information is routed through routing tables, you may have anywhere from 50 to maybe as many as 300 hops before you get a response. It's an engineering issue. It's a very fundamental engineering issue. And until you really understand the fact that internet imposes on you hops, you cannot just go and start designing systems, because the system will not work. Or they will work, but nobody wants to wait 4 seconds or 15 seconds for a simple answer. And therefore they will go and build a local system that will give them an answer immediately. So if you want to do a transformation, if you want to have a data warehouse, if you want to have a data warehouse which is globally accessible, you have to start thinking about the speed of how you're going to get from point A to point B. Now, one of the ways of doing this thing, of course, is to design a network where you design the network centrally, then put out at the various locations in the world, depending on need, so-called edge computing capabilities. By the way, this is the design of Google. Google has the unbelievable capability of, by and large, responding to egress anywhere in the world in 0.24 to 0.25 to 0.30 seconds. In other words, you have sub-second response time anywhere, and by the way, you will get 10,000 to 15,000 answers to your inquiry. You have to start thinking now about a system that is massively distributed but centrally organized. And that means that you have to start thinking about an information network for the gig that will do this sort of thing, that will be governed by the ability to give a soldier in Iraq on a Humvee the same response time locally based on data that was located in Arlington, Virginia, as if that data would be in the Humvee locally. That's a tough engineering design issue. So what you really need then to do is to design the network in ways where the internet and the local firewall protects the local environment, reaches the support that the network provides, but that's as much as it does. And that means that it can do the following, and I perhaps best illustrated by using Akamai, which is the closest example I have to Google. Akamai has 18,000 servers, and they do support of what's called edge caching and edge computing. And that means that you can then take a slice of that network and extract support for that slice that you want to support. That means that you must be able to bridge the information service provider to the backbone of the network whenever network congestion occurs. And you then must take the detection of virus, worm, and hacker out to the edge machines where it can be identified and blocked without having access to the central database. It's a tough order, a tough problem, but I'm just telling you very briefly, and there will be more discussion about it when I will be discussing the network design next time. But I want to point out that Akamai is a prototype of a network design that is both centrally massively parallel and highly distributed. And the benefits, of course, is security, because anytime you touch the whole area of internet and using internet as a means of communication, you have a problem with security. And that means you really have to create the places where you're going to have your first, second, and third line of defense before the pollution, before the attack is going to come into the central environment. I don't want to get into the details now, except to leave you with an idea that the way as I see the gig architecture is to see it in terms of two kinds of systems, an unclassified and a classified system. The red is classified. And again, as you see, the underlying basis is below this diagram. It shows the underlying infrastructure, and then the applications are just floating on top of it. So the idea then is to have an architecture which is highly distributed, highly modular, but based on highly centralized computing. Let me apologize for the speed with which I treated rather glibly my last three discussions about networking. It's a vast, complex issue. But let me just leave you now with a summary of my presentation. If you want to do a transformation, you must consolidate applications and data center operations. You cannot afford having thousands and thousands of applications. You cannot afford having hundreds and hundreds of data centers out there. Now, once you have the thing consolidated, you can then create what's called edge computing to provide the response characteristics. But the fundamental architecture is one of consolidated infrastructure. The infrastructure must be streamlined, consolidated, because that's the only way how you can suck out the cost, which are today killing the entire system. The defense gig is the concept for delivering net-centric capabilities. It is clearly the direction in which we are going, although I must tell you the final definitions of what gig is all about still remains a bit of a mystery. It is seen by various people in different ways. There are various schools of thought how to implement gig. Clearly, one of the schools of thought is to leave the applications in place and just go through a very complicated discovery process by which you can bridge the applications. Whether that is feasible or not remains to be seen. I don't believe it's feasible. Nevertheless, the gig is on the table. It is the direction in which the Department of Defense wants to transform itself. And so now the issue is one of security and high responsiveness. Security, in fact, is correlated with high responsiveness and vice versa. High responsiveness means extremely rapid response on a tactical level, and locally supported, local servers supporting particular needs, while at the same time the applications and the underlying thinking of the gig is centralized and centrally managed. This then concludes the presentation.